right, and hello to Chem 400 office hours. I am ready to get into anything you have questions on. We can talk about all of it in the next hour. I checked my emails earlier. I haven't received any submissions over email, so whatever shows up live, that'll be the office hours. I guess this is the last October office hours, which has got to make this the Halloween edition. Oops. Awesome. That is what I signed up for. This one is a spooky one. Alrighty. All right, so we have hydrogen, argon, and oxygen are added to an evacuated 150 milliliter flask. Hydrogen was stored under 5.0 times 10 to the first. Sorry. Wait, actually, that's not the pressure, that's the volume. All right, so they give us a bunch of initial conditions for hydrogen, argon, and oxygen. They give us initial volume, there we go. So they give us initial volume for hydrogen. It's 5.0 times 10 to the first milliliters. And initial pressure, 750 torr. Argon was stored in a 75 milliliter flask with a pressure of 450. And then oxygen was stored in a 100 milliliter flask under a pressure of 350 torr. All right, so that's our given information, and then they ask the big question. Determine the pressure of, or sorry, I should say, the pressure in the 150 milliliter flask. All right. So here's the deal. So let me just look over this to make sure I didn't miss anything. All right. So here's the deal. This this problem is actually a combination of well, it's primarily going to use Dalton's law of partial pressures, because we want to know the pressure in the flask, and this is going to be the total pressure. It's the pressure of a mixture of gases. Dalton's law of partial pressure tells us that the total pressure of a mixture of gases is the pressure of each, the partial pressure of each member of that mixture added up. So it'll be the partial pressure of hydrogen plus the partial pressure of argon plus the partial pressure of oxygen. All right, so this is how we find our answer. This pressure right here is this pressure right here. Now, it would be incorrect to take these given pressures and add them up, because these are not the pressures of each gas inside the 150 milliliter flask. These are the pressures of each gas inside their initial starting containers, which have a variety of volumes. All right, so Here's the deal, though. So we need to find these partial pressures. And for each one of them, we're given an initial volume, an initial pressure, but we're actually given one other piece of information. Right here, we actually know their final volume. Because we know hydrogen, for example, starts in a 50 milliliter flask, but ends in a 150 milliliter flask. And so with V1, P1, and V2, we can actually use a version of the combined gas law, right? We know that the combined gas law is P1, V1 over N1, T1 equals P2, V2 over N2, T2. All right. In this case, moles and temperature are held constant, so we just have P1, V1 equals P2, V2, and we know there we go. We know P1, we know V1, and we know V2. This equation lets us solve for P2, and we can do this for each individual gas. This will be the pressure of H2, the pressure of O2, and the pressure of argon that we want to add together to find our total pressure. So we're going to use this equation 3 times, once for each once for each gas, find our partial pressures, add them all at the end. So that is the master plan. All right, let's begin with a little bit of algebra. So we've got P1, V1 equals P2, V2. We're going to begin. We want to find our final pressure, so we'll divide both sides by final volume. And we get a reworked expression. Final pressure is equal to initial pressure times initial volume over final volume. All right. So we're going to use this equation and knock it out for each gas. So let's go ahead and start with hydrogen, H2. We have our partial pressure of hydrogen is equal to P1, which is 750 torr, times V1, which is 5.0 times 10 to the first milliliters, over V2, which is 150 milliliters. You'll notice that milliliters cancel. And I'm going to grab my calculator to crunch my numbers. 750 times 50 divided by 150 comes out to, whoops, sorry, I want that in black. 250 torr. One of the things you'll notice is all the numbers we used have 2 sig figs. Our answer is 2 sig figs, so there's no reason to round. Let's look at argon. So argon's initial pressure was 450. not just 450, excuse me, but 450 torr. We always got to include units. Its initial volume was 75 milliliters. And its final volume is 150. As before, volume cancels. Now we get 450 times 75 divided by 150. All right, here, the answer we get is 255. But you'll notice, again, all of our numbers have 2 sig figs. We got to round to 2 sig figs. I'm going to wait to round to the end. You always wait to round to the end of the problem, but I'm putting these 2 lines here to remind myself that this number has 2 significant digits. Let's take a look at oxygen. The partial pressure of oxygen is equal to its pressure, 350, times its volume, initial pressure times initial volume over final volume. Milliliters cancel. We get 350 times 100 divided by, 350 times 100 divided by 150. There we go. This comes out to be 233.33 forever, actually. But like our previous problems, we're actually limited to 2 sig figs. Our initial pressure actually has 3 significant digits, but you got to roll with the fewest. So putting those 2 lines there to remind ourselves this number is 2 sig figs. We are all set up to calculate our total pressure because it is the sum of these 3 partial pressures. And again, all these numbers have 2 sig figs. So you add these all up, our total pressure is 708.33. But you'll notice, so we added these numbers, the last significant digit in each of these is in the tens place, which means we need to round to the tens place. 8 rounds up, so our final answer is 710 torr. And that is the pressure inside this flask. So, Julia, I actually got an email right before I stepped into office hours um, from another faculty giving me a heads up that there was a typo um, on exercise 7. I think is the one that this comes from. And I didn't get it. I haven't had a chance to read it because I was literally opened up my email right before, and I saw a title that said subject that said typo on exercise 7. So my guess is that this is the problem that has the typo in it. So you should know. Well, one, good job, you did this problem correct, and two, I'm going to go back and you will totally get full credit for this problem. So there's a happy ending to this thing. Solid. Okay, Amanda, you've got a question. Let's see. All right, so let's take a look at this guy. So we have a sample of nitrogen gas with a volume of 0.250 milliliters at a pressure of 0.967 atmospheres. What will the volume be if the pressure is increased to 1.65 ATM? All right, now, Amanda, this is actually a very similar problem to the one we just did. We've got initial pressure and volume is equal to final pressure and volume. And this one, we are trying to find that final volume. So we're going to divide both sides of this equation by our final pressure to get it to cancel. We get final volume is equal to initial pressure times initial volume over final pressure. And now we plug in our numbers. We got 0.967 atmospheres times our initial volume, 0.250 milliliters, over, where was, oh yeah, there's our final pressure, 0.65 atmospheres, 165 atmospheres. Atmospheres cancels. Now we're ready to punch in our numbers. .967 times 0.250 divided by 1.65. So let's see, it comes out to be 0.1465151. That keeps going for a while. We don't have to, however, because you'll notice that every number used in this problem has 3 sig figs. So we can only have 3 sig figs. 5 is going to round up. And so our volume will be 0.147 milliliters. Amanda, let me know if that makes sense. Okay. This is an interesting problem. So we're told that the density that at STP, which for the record is pressure of 1 atmosphere and 0 degrees Celsius or 273.15 Kelvin. So that STP, the density of this gas is, what was it, 1.43 grams per liter. And we're told to calculate the density when the pressure is 743 torr and the temperature is 26 degrees Celsius. All right, so whenever you start, this problem looks bewildering, right? How are we going to possibly calculate this? Well, start with what you're trying to find. All right, what are we trying to find here? We want to find density. All right, now what is density? Density is equal to mass over volume. It's a ratio of mass to volume. So we need two things. We need to know the mass and the volume of this gas at, these two at pressure 743 and temperature 26. All right, now let's look at what we're given. We're given our pressure. When we're given, I'm just going to call it P1, is 1 atmosphere. We're given T1 is 273.15. And we're told that our density here is 1.43 grams per liter at these initial conditions. And we're also told that our final conditions, right? That we want to know what the density is when we're at a pressure of 743 torr and a temperature 26 degrees Celsius. All right. Now we know we're dealing with a gas, right? So we're going to need to use one or two, possibly, of our gas laws. The first one to look at is PV equals nRT. Now there's a trick. You'll notice for both sets of conditions, We know our pressure, we know our temperature, and we know R. Which, looking at this, you might go, well, that's still leaves us two unknowns. Oops, excuse me. Sorry, my headphone's getting pulled out. Now, there's a trick you can do with PV equals nRT. Oh, wait, hang on. Oh. There we go. Where you can, if you divide, excuse me. If you divide both sides of this expression by VRT, RT cancels on this side, volume cancels on this side, and you get a rearranged expression, moles over volume is equal to pressure divided by R divided by T. And here's the thing, we know the pressure, the temperature, and R. So we can solve for the moles over volume. And you'll notice that this expression is surprisingly similar to density. Right? Density is the mass per volume ratio. This is the moles to volume ratio. In fact, the only difference between density and moles per volume, so there we go. There we go. Density is equal to mass over volume. And we have an expression where we have moles over volume is equal to P, pressure over R, times T. You have to ask yourself, what is the relationship between moles and mass? And that relationship is if you take your moles and multiply by the molecular weight, it equals your mass in grams, right? If you know your, now we don't know the molecular weight here of this particular gas yet. We don't know, but we have this expression where we have moles times molecular weight equals mass. So if you substitute this in to your equation for density, that would be density is equal to moles times molecular weight over volume. Now I'm going to algebraically rearrange this a little bit. Moles over volume times molecular weight is equal to density, right? So we have a new expression, density is equal to moles over volume times molecular weight. And check this out. We do not know what our molecular weight is. But we do know what our density is. We're given our density, and we can solve for what our moles over volume is equal to because we know pressure and temperature. All right? So we are going to use this to solve for molecular weight, and then we're going to use our molecular weight to determine the density at the new pressure and temperature. So we have our moles over volume is equal to P over R times T using our initial conditions, so our P1 and our T1. Our initial pressure was 1 atmosphere because it's at STP over R, which is 0.08206 liter atmospheres per mole Kelvin. And then our initial temperature at STP, 273.15 Kelvin. Kelvin cancels, atmospheres cancel. Now we got to crunch our numbers. So our moles over volume is equal to 1 divided by 0.08206 divided by 273.15. This comes out to be 0.0446. Our units are moles per liter. All right, now flashing back really quick. We have that expression that we derived, density is equal to our moles per liter, over volume, times our molecular weight. Now we know our value for this. We know our density, it's given right there. So now we solve for our molecular weight. So molecular weight is equal to our density over our mole to volume ratio. Our density is 1.43 grams per liter. Our mole to volume ratio is 0.0446 moles to liter. There we go. 1.43 divided by 0.0446. So our molecular weight comes out to be 32.06. We can only keep 3 of these sig figs. Oops. And our units here are grams per mole. You'll notice that the per liter cancels. So this is our molecular weight. Here's why we need it. Because so again, flashing back to the equations we derived, we know that density is equal to the mole to volume ratio, it's this guy right here, our density is equal to our mole to volume ratio times our molecular weight. Now we know this. We need to calculate the new mole to volume ratio based on this pressure and temperature, and then we'll be able to calculate our density. All right, so let's hop to it. First off, we need to calculate our mole to volume ratio at our new pressure and temperature. And this is where we run into our first problem. We have our value for R is 0.08206 liter atmospheres over mole Kelvin. Our problem shows up because our pressure here, where we're supposed to calculate our density, is in torr. Torr doesn't cancel with atmospheres, and Kelvin doesn't cancel with degrees C. So we have to do a couple unit conversions. First, 743 torr to atmospheres. There are 760 torr in 1 ATM. So 743 divided by 760 comes out to be 0.978 atmospheres, and then our temperature, to convert from degrees Celsius to Kelvin, you add 273.15 . So this is 299.15 Kelvin. The last sig fig here would be in the ones place due to our 26. Now with these numbers converted, we can punch them in. So we got 299.15 Kelvin. Oops. Oh shoot, I need my pressure. Just 0.978 atmospheres. Because we've done our unit conversion, atmospheres cancel, Kelvin cancels. We are ready to calculate our mole to volume ratio. So 0.978 divided by 0.028206 divided by 299.15 comes out to be 0.0398. And our units are moles per liter. Again, the reason why this is crucial is because our density is equal to our mole to volume ratio times our molecular weight. Which I believe our molecular weight was 32.1. Yeah. So density is equal to our mole to volume ratio times molecular weight. Our mole to volume ratio is 0.0398 moles per liter times our molecular weight, which is 32.06. 3 sig figs, and this is grams per mole. One thing you'll notice, moles cancel with moles, leaving us with grams per liters, which is a unit of density. So 0.0398 times 32.06. I'm initially getting 1.275988. We're rounding to 3 sig figs. 5 rounds up. So our density at the new temperature and pressure would be 1.26. No, sorry, 2.8 grams per liter. So it was deceptively simple, but this is kind of a monster problem. Again, very on brand for Halloween. And it was, kind of a beast of a problem. Yeah, Julia, it would be exactly the same. It would be exactly the same setup. Just it'd be different with the where you plug in stuff. But all the algebra, all the steps would be 100% identical. Yeah, no, Julia. So this is actually the perfect problem to end on. This is not going to be um, too bad. Actually, working this way is a lot more direct. You'll see. So here we're asked to calculate the density of carbon dioxide gas in grams per liter. And we're given our temperature is 35 degrees C. Pressure is 4 atmospheres. And we're given R. All right, so again, and actually one of the things that'll help this go a little faster is we just did a problem where we rearranged PV equals nRT so we just used PV equals nRT to algebraically find the ratio of moles to volume, right? We know moles to volume is equal to pressure over R times temperature, right? And we know that this moles per liter is very closely related to grams per liter, right? We just have to use the molecular weight of our gas, and since we know CO2, we can get there fairly quickly. The one detour we have to take is we need to convert our temperature from Celsius to Kelvin. So this will be 308.15 K. But now we can punch them in here. Pressure is 4 atmospheres. Oops. Four atmospheres, R is 0.08206 liter atmospheres per mole Kelvin, times T, which is 308.15, and atmospheres cancel, Kelvin cancels. So our mole to volume ratio. Let's see, we got some numbers to crunch. 4 divided by 0.082. Oh wait, hang on. 4 divided by 0.08206 and 308.15. Gives us a mole to volume ratio of 0.158 moles per liter. All right, and like we said, we're almost there. We just need to multiply. We need to remember that this is moles of CO2 gas, and what we need to do is convert moles of CO2 to grams. And we can calculate the molecular weight of CO2. Carbon is 12.01. Oxygen is 16.00. We've got two of them. So this comes out to be 44.01 is carbon dioxide's molecular weight. Now moles of CO2 cancel, and you'll notice we are now in grams per liter, which is our units of density. So we multiply this by 44.01. And this comes out to be 6.96 grams per liter. Alrighty, and so that's that problem. It is 4:01. So I've got to bounce. I've got a 2-year-old who's awake and up from his nap. But this is a really good office hours. We did a lot of really gnarly problems, perfect for our Halloween edition. Hope you all have a great weekend, and I will catch you next week.